This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the introduction to thumb instruction set in ARM process. The slides are prepared by referring the textbook ARM System Developers User Designing and Optimization System Software. Authors are Andrew. Now, what is thumb is? A thumb is a compressed 16-bit representation of a subset of ARM instruction set. It is primarily to increase the code density, increases performance in some cases. It is not a complete architecture. All thumb-aware codes also support the ARM instructions. Therefore, the thumb architecture need only support common functions. The thumb bit, to differentiate whether ARM processor is in thumb mode or non-thumb mode, we have a control bit called as T bit in CPSR, current program status register. The T bit in the CPSR register controls the interpretation of the instruction stream. The switching from ARM to thumb or thumb to ARM by executing the BX instruction, which is branching instruction. The exceptions also caused switch to ARM code written symmetrically to ARM or thumb code. Here, the T bit in MSR we are not going to change. Do not change the T bit with MSR register. The thumb programs model. In this, the total registers from R0 to R15 which are exist in the ARM processor, which we have the access for R0 to R7, that is L0 registers for thumb mode, whereas R8, R9, R10, R11, R12, these registers we have a restricted access in the thumb mode. The R13 registers will act as stack pointer. R14 register will act as link register. R15 is a program counter. Apart from these 16 registers, we have one CPSR register, that is current program status registers. These are the register set of thumb program model. The thumb registers use R0 to R7 are general purpose register. R13 is used implicitly as stack pointer. In ARM code, this is a software convention. R14 is used as a link register implicitly as in the ARM instruction set. Few instruction can access the registers R18 to R15. The CPSR flags are set by data processing instructions and control conditional branches. The similarities between the thumb and ARM are the load store architecture with a data processing, data transfer and control flow instruction. It support for 8-bit byte or 16-bit offword or 32-bit data types. Offwords are aligned on 2-byte boundaries, whereas words are aligned on 4-byte boundaries. The 32-bit unsegmented memory. The differences between a thumb and ARM are: most thumb instructions are unconditional. All ARM instructions are conditional. Most thumb instructions use two address formats, whereas most ARM instructions use the 3 address format. For passing the arguments, we have to pass 3 values for ARM instruction, whereas for thumb instructions, we have to pass 2 arguments or 2 operands. Thumb instruction formats are less regular as a result of dents in the encoding. Thumb has explicit shift opcodes. ARM implements shifts as operand modifiers using barrel shifter. The original thumb implementation translated the opcodes into ARM opcodes. This means the effect of thumb and ARM instructions are the same. Thumb is more restricted. Example, smaller offsets and the immediate data. 1 or 2 new functions. Example, the branching instructions like BL. Later, implementation decode thumb directly. So, the figure shows the decoding of thumb instruction. For the add instruction, we are seeing using a decoder. Each thumb instruction is translated to 32-bit instruction and the thumb are 16-bit instruction. This figure shows a simple thumb add instruction being decoded into an equivalent ARM add instruction. So in the thumb instructions, you can say 2 addresses space only, R0 and immediate data, that is #3. Whereas in ARM, we are going to have 3 address space, R0, destination, source R0 and immediate data #3. The CPSR registers consist of various flags. The figure 3 shows thumb instruction mapping. For add RM, immediate 8, which is consist of a 16-bit data, this will be converted into the 32-bit format as follows. The immediate data, which is of 8-bit size, it is converted into the lower bits as immediate 8 bits from bit 0 to bit 7, whereas bit 8 to bit 11, it is appended with zeros. Next, the registers which we have placed in the operand positions in the thumb instructions as source as well as destination, this will be copied into 2 locations because the address space for ARM is 3 address space. This is immediate data, this is source register and this one is destination register. As we have seen in the earlier case, add R0, hash some immediate data, this will be converted into add S R0, R0, hash immediate. So the immediate data, it is placed from bit 0 to bit 12, that is 12-bit offset, followed by RD register, followed by RD registers, which will map the 2 address space into 3 address space. The next one is the opcode. The corresponding opcode, it will be placed into the bit 20 to bit 24. The last 3 bits, which is like move, compare, add, subtract with immediate, this will be converted into its equivalent code from the bit 25 to 27. Whereas this always condition will be placed from the bit 28 to bit 31. So this is how the mapping of thumb instruction set, which is of 16-bit size, will be converted into ARM format, which is of 32-bit size. The various thumb applications are, the thumb code properties are 70% of the size of the ARM code, 30% less external memory power, 40% more instructions. With 32-bit memory, ARM code is 40% faster than thumb code. With 16-bit memory, thumb code is 45% faster than ARM code. For best performance, use 32-bit memory and ARM code. For best cost and power efficiency, use a 16-bit memory and thumb code. In a typical embedded system, use ARM code in 32-bit on-chip memory of small speed critical routines, whereas the thumb code in 16-bit off-chip memory for large non-crucial control routines. These are the various applications which we can use for ARM processors as well as in thumb mode as well as ARM mode. Now coming to the instructions of thumb instructions. The first thumb branch instructions we will see. Branch, condition, label. Simply branch label. Branch BL label, BX RM. These are similar to ARM instruction except offsets are scaled to offward, not fullward. Range is reduced to fit into 16 bits only. BL works in 2 stages. The assembler generates both offs. The LR bit 0 is set to facilitate return via branch B. The next instruction is BX instruction, which is branch and exchange. This is to return to ARM or thumb. It is for branching from thumb to ARM or ARM to thumb. The syntax of the instruction is BX LR. This LR register will hold the address of the switching program. This can be replaced. It is same as that of moving LR register to the program counter, which will execute the current instruction. So when it is branching from program 1 to program 2, whatever the address of the first instruction of program 2, that it will be stored in program counter. So in the BX, we are going to be placed the address which is in link register that will be copied from LR register to PC, which will control will be transferred from main program to sub program or thumb program whenever you are switching from one to another. Subroutine calls. Later ARM supports BLX instruction. To synthesize BLX instruction or earlier ARM, add R0 comma sub R plus 1. Plus 1 it is for to enter into thumb mode. Add LR comma return. This is for to return address to be saved in link register LR. Next BX R0. This is for calling to a subroutine return. The next category is thumb data processing instructions. The data processing instructions manipulate data within register, includes move, arithmetic, shifts, logical, compare and multiply instructions. The thumb data processing instructions are subset of ARM data processing instructions. In the table 1, we have instructions corresponding to move operation, that is MOV and MVN instruction. MOV instruction, this instruction is used to move a 32-bit value into a register. The value of the register or immediate data that I am taking as N, that will be copied into the destination location RD by using move instruction. MVN instruction, which will move the complemented 32-bit value into a register. So the value whichever we have placed in the immediate or register, that will be complemented, that is not operation, and the result will be stored in RD register, which is a target here. The next set of instructions are related to arithmetic instructions. The table shows the various arithmetic instructions supported in the thumb mode. Add instruction. This is for addition of two 32-bit data. Here The register contents RN, RD will be added with some immediate data or register. Wherever I am placing N, it is corresponding to an immediate data or any another register. The contents of this N will be added to RD and the result will be stored in RD register. ADC instruction. This instruction, it is for adding two 32-bit data along with carry flag which is exist in the CPSR. The instruction will execute by adding the contents of RD register with the value of immediate data or register which you have placed in the N location along with the carry flag, and the result will be stored in RD register. The next instruction is SUB, which is a subtraction of two 32-bit data. Here, the contents of immediate data are registers which are placed in N location that will be subtracted from RD register and the result will be stored in RD register. SBC. SBC, it is for subtraction of two 32-bit data along with the carry flag. The functionality of this instruction is the value of immediate data R which you are representing as N that will be subtracted from RD register along with the carry flag and the result will be stored in RD register. The next one is MUL instruction which is multiply two 32-bit data. This instruction will multiply the RD register contents with an immediate data or a register contents which are of 32-bit size, and the result which is product is 32-bit size that will be placed in RD register. The syntax of the instruction is opcode placed by RD and N, where N can be an immediate data or through any register RM I can take. Always thumb instructions will support only two address spaces. The next category belongs to logical instructions. The table 3 will use the logical instructions supporting the thumb mode in the ARM processors. The various logical instructions supported are AND, which is logical bitwise AND operation of two 32-bit value. It will perform a bit by bit AND operation between RD register and immediate data or RM register which you are placed in N place, and the result will be stored in RD register. The next instruction is BIC, which is a logical bit clear instruction which will perform the AND followed by NOT gate of two 32-bit value. Here, the contents of first operand will be ANDed with the complement of the second operand, whether the second operand can be an immediate data or it can be through any registers which I am placing in the place of N value. So these two will be ANDed and the result will be placed in RD register. The next instruction is EOR instruction, where EOR instruction will perform the logical bitwise XOR of two 32-bit values. This instruction will perform a bit by bit exclusive OR operation between the register RD and the N value, where N is an immediate data or any register RM, and the result will be copied into RD register. The next instruction is NEG, which is for negate, which will negate the 32-bit value which are placed in N. This instruction will perform negation, which is nothing but the subtraction of the N value, either it can be an immediate data or register RM, will be subtracted from 0 and the result will be stored in RD register, which will use usually the 2's complement of N value. ORR, which is logical OR instruction. So this instruction will perform logical bit by bit OR operation of two 32-bit values. This instruction will perform bit by bit between the register RD and N value, where N can be an immediate data or register RM, and the result will be stored in RD register. The next instruction is TEST, which is for test. This instruction is used for test bits of an 32-bit value. This instruction will perform the AND operation between the RD register and N. N can be immediate data or and register RM, and this will not store the result anywhere. It will just affect the flags which are existing in the CPSR register. The syntax of the instruction is instruction opcode followed by RD and N, where N can be an immediate data or it can be any register RM. The next category instructions are compare and shift operations. The table 4 lists the various compare and shift instructions supported by thumb mode. CMP, which is used for comparing two 32-bit values. This instruction will compare the register contents Rn with the value of N, where N can be an immediate data or register M. By comparing these two values, if Rn contents R is equivalent to N, then 0 flag will be set 1. If Rn register contents is greater than 1, then the carry flag is equivalent to 0. If Rn register contents are less than N, then it will make the carry flag is equivalent to 1. In all these cases, the Z flag is equivalent to 0. The next instruction is CMN instruction, which is used for comparing the negative of two 32-bit data. This instruction will do the complement of the second data. It is same as that of, for comparison, we do Rn minus N. This is for compare instruction. So in CMN instruction, we are going to be compare Rn and complement of N, which is nothing but complement of complement will become plus. So that we will take as Rn plus N. Based upon the result, it will affect the flags. The next instruction is ASR, which stands for arithmetic shift right. Here, this instruction will shift the contents of Rn register towards a right side by the number of bits which you have specified in N. Usually N will be an immediate data or through register Rm, and the result will be stored in RD register. The MSB, whenever you are shifting towards right, it is going to be insert logic 1. LSL it is for logical shift left. Here the contents of Rn register will be shifted towards left side depend upon the value of N. Either N can be an immediate data or through Rm, and the result will be stored in RD register. LSR register, which is logical shift right. Here the contents of Rn register will be shifted towards right side by N bits or N whichever you have specified as immediate data or through registers, and the result will be stored in RD register. The next instruction is ROR. This ROR instruction rotate right a 32-bit value. Here this instruction will rotate the register contents RD by N number of times, and the rotated value will be loaded in RD register again. The next set of instructions are corresponding to load store instructions, that is LDR and STR for thumb mode. LDR, which is load word into a register. This instruction is used to store the 32-bit value which are there in the memory location whose address is specified here, that will be stored into RD register. STR, it is for save word from a register. This instruction will copy the contents of register into the memory location whose address is specified in the instruction, and the size of data here it is 32-bit size. The next instruction is LDRB, which is load byte into a register. This instruction will copy the 8-bit of data from the memory whose address is specified in the instruction. That memory contents will be placed into the RD register. The size of data which we are transferring here it is 8 bits. STRB, which is save byte into a register from a register. So this it is used for storing the register RD content into the memory location whose address is specified in the instruction, and the size of the data here it is storing is 8-bit size. Next, LDRH. which is load upward into a register. Here, this instruction will copy the 16 bits of data from the memory into RD register. The next one is STRH, which is for save upward from a register. This instruction will copy the register contents RD into the memory location whose address is specified in the instruction and the size of the data which it is transferring is. Next one is LDR-SB, which is load a signed byte into a register. This instruction will load the sign extended the data in the memory whose address is specified in the instruction of 8-bit size that will be copied into RD register. The next one is LDR-SH, which is load a signed upward into a register. This instruction will copy the sign extended memory contents whose address is specified in the instruction and the size of the data is 16-bit into the register RD. The next one is multiple register load store instruction. The thumb version of load store multiple locations are reduced from ARM load store instructions. They only support increment after addressing mode. Pre-indexing is not supported here. Only it supports increment after addressing mode only. LDM, this instruction, it is used for load multiple register. The syntax of the instruction is LDM, increment after addressing mode, RN, exclamation mark, comma, low registers. Here, the contents of the registers from RN to 4N registers, these contents will be stored in RD register. How many registers we have placed, that many number of registers will be affected because it is multiple load registers. You can have multiple registers will be loaded here. Next one is STM, which is save multiple register. This instruction, STM, save multiple register. This instruction syntax is STM IA RN exclamation mark low registers list. Here, the RD registers with N value, that is N registers, will be stored into the memory location whose address is given with RN plus 4N register. Rn is equivalent to Rn plus 4n for every iteration. N is the number of register. Base register is Rn updated after execution. The thumb stack operations are different from the equivalent ARM instructions because they use traditional push and pop concept. Push registers onto the stack. Push low register, comma, LR. This instruction will copy the contents of RD registers multiple N bits into the memory location whose address is given with the stack pointer. How many memory locations we are taking? As it is 32-bit, each memory location is 4-bit, so 4N size. Stack pointer, for every push operation, the stack pointer will be decremented by 4 times of the registers. Pop registers from the stack. This instruction is used to pop the contents from the stack. The syntax of the instruction is pop the low register, comma, PC. Here, the memory contents from the stack, each register will hold 32-bit data, that is 4 memory location, will be popped into the RD register. If it is multiple, you can have N value. Thumb software instruction. The thumb SWI operate exactly like the ARM SWI instruction, software interrupt instruction. It differs in software interrupt number and limited to the range 0 to 255 and not conditionally executed. If any interrupt or exception flag is raised in thumb state, the processor automatically revert back to ARM state to handle the exception. The syntax of the instruction is SWI hash immediate, where immediate will use the type of the interrupt SWI. Here, this instruction will copy the address of the next instruction followed by SWI into link register supervisory mode, that is LR-SVC. The CPSR current program status register will be copied into saved program status register in the supervisory mode. The program counter will be loaded with the vectors plus default offset value as 8, and the mode of operation for CPSR will be changed to SVC. As it is IRQ interrupt CPSR, the ith bit will be set to 1. For ARM state, the CPSR, the thumb bit will be equivalent to 0. Example, SWI call with 45 as SWI number. The offset value we are having at 8000H with SWI instruction. This is the address of the SWI instruction in the program code. Typically, the SWI instruction is executed in the user mode. So before executing SWI instruction, the CPSR is in user mode. Now this CPSR will be changed to SVC mode. Whatever the previous CPSR values are there, these will be stored in SPSR without any changing. As it is thumb mode, the T bit will be set to 1. Next, the PC, current PC value is 8000H. This will be copied with a new address, that is 00008, which is the address of the ISR can have. The link register, previously it is having some random value, assume it is 003FFFFF. After executing this SWI instruction, again the control has to be executed, the instruction which is followed by SWI, that address will be loaded into LR register, which is equivalent to 8042. R0 register will contains the 12H, which is the address of the type of the software interrupts. Thank you all. So in this lecture, we have discussed the introduction to a thumb mode and the differences between thumb mode and ARM mode, and various instructions which are supported in the thumb mode. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.